I'm focusing on understanding the lasso regression technique and how it's used to analyze data. Specifically, we'll examine the scikit-learn's lassopath function. We're using the lassopath function in scikit-learn, a popular machine learning library in Python. This function helps perform lasso regression and returns information on the regularization parameter, alpha, coefficients, how much each variable matters, and duals, another important concept we'll explore. The key here is understanding how the change in the regularization parameter influences the coefficients. This is our core question. We're given the output of lassopath and we need to deduce what it implies about how lasso regression works. We need to carefully consider what happens to the coefficients as the regularization strength increases. I think about what the regularization parameter, alpha, does. A higher alpha means stronger regularization, forcing the coefficients to shrink more towards zero. Some coefficients, the less important ones, hit zero first. That's true. The duals aren't the residuals, the errors of prediction. They're related to a more complex mathematical concept in optimization, so I'm saying this is false. If a coefficient becomes exactly zero, that means the associated feature is eliminated from the model. So, yes, lassopath does feature selection. In lassopath, alpha values usually go from high to low. Therefore, this statement is false. I'm using scikit-learn's lassopath function, a powerful tool for performing lasso regression. It's all about finding the best fit line while keeping things simple by reducing the complexity of the model. Think of it as a way to streamline things, eliminating unnecessary details. Lasso stands for least absolute shrinkage and selection operator. It's a type of regression that does feature selection, choosing which variables are important to include in your model and discarding those that don't contribute much. The lassopath function gives us the regularization parameters, alphas, coefficients, cofs, and dual coefficients, duals. This is absolutely correct. That's the beauty of lasso. As we crank up the regularization parameter alpha, it pulls all the coefficients towards zero. But, some coefficients are more sensitive to this and get squeezed to zero faster than others. It's like tightening a nut on a bolt. All the nuts might tighten but some could be tighter than others. Exactly, that's one of LASSO's superpowers. When a coefficient gets shrunk to exactly zero, we're essentially removing that corresponding variable from our model. We're performing feature selection by setting those coefficients to zero. Not quite. I've seen that lassopath typically outputs alphas in descending order, meaning starting with a high alpha then gradually decreasing it. Think of it as systematically exploring different levels of regularization to find the sweet spot. It's a common misconception. We start with a dataset. This data will be used to train a lasso regression model. Think of it as the ingredients for my recipe. I'll adjust the alpha parameter. Alpha controls how much I shrink the coefficients towards zero. A higher alpha means more aggressive shrinkage. It's like controlling the heat on my stove. Higher heat makes everything shrink faster. As I increase alpha, I'll see some coefficients shrink all the way to zero. This is like throwing away some ingredients that don't improve the dish. It's automatic feature selection. Lasso does it for me. After the lasso regression process, I get three things. The coefficients, how much each feature contributes, the alphas I tested, and the duals, a measure relating to optimization, not residuals. Think of it as my recipe's final stats, including ingredient amounts, the temperatures used, and a measure of how well balanced it is. I use the lasso, least absolute shrinkage and selection operator, algorithm. Lasso uses L1 regularization. It adds a penalty to the model's complexity based on the absolute value of the coefficients. It helps prevent overfitting by shrinking the impact of less important features. This acts as a kind of feature selection, picking only those features deemed most important for fitting the data. It's like using a special recipe to ensure the most important ingredients are prominently featured. This is the question which I am asked to answer. It asks about understanding lasso regression, specifically about what happens when I increase a certain parameter, alpha, during the model fitting. This statement is false. The duals are not the residuals. They represent something else related to the optimization process of the algorithm, and not directly the prediction errors. This statement is true. The fact that coefficients become zero is, by definition, feature selection. I am removing those features from my model because they don't contribute significantly. This is false. The alpha values are typically sorted in descending order, from largest to smallest. This statement is true. Increasing alpha increases regularization strength. All coefficients shrink, but those less important to the model reach zero first. The overall topic, focusing on how the lasso regression model's coefficients behave when the alpha parameter is increased. This describes the overall lasso regression process. The steps involved in the algorithm, from data input to output. I see. Lasso path process. As the core of this question, we're using scikit-learn's _lasso_path function, which is a powerful tool for lasso regression. It's like a path through different levels of regularization, showing how our model's coefficients change as we increase the regularization strength. At each step, we're finding coefficients and duals. The output of lasso_path includes three key components: alphas, coefficients, and duals. Alpha controls the strength of the regularization, coefficients reflect feature importance, and duals are the solutions to the optimization problem. This function directly relates to the problem statement and options A and C. Let's talk about the lasso regression algorithm itself. It's a type of regression that performs regularization using L1 penalty. This means we add a penalty term that is proportional to the absolute value of the coefficients. The strength of this penalty is controlled by alpha. As alpha increases, it encourages coefficients to shrink towards zero. This is what's happening in options A and C. The core question is, what happens to the coefficients when we crank up the regularization strength, alpha, during lasso regression? We're analyzing the behavior of coefficients in response to a change in the regularization parameter. We are focusing on how the increase in alpha impacts the coefficients. That is the crux of the entire exercise and is directly connected to the multiple choice answers given. The question focuses on using scikit-learn's _lasso_path function. For lasso regression, I would say that this is crucial for understanding how lasso regression works, and how it computes its alpha, coefficients, and duals. Remember that this function gives the alphas, coefficients, and duals as output, which are discussed in the other parts of the question. The output of _lasso_path gives us alphas coefs and duals alphas represent different regularization strengths. Coefs are the coefficients of our model for each alpha. These are the focus of the question and directly relate to options A and C. Finally, duals are related to the optimization problem, which is described in option B. Understanding the interplay between these three outputs is essential for grasping the problem. I'm using scikit-learn's lassopath function, which is a powerful tool for performing lasso regression. Lasso stands for least absolute shrinkage and selection operator. It's a type of regression that uses a penalty term to shrink coefficients toward zero, helping in feature selection. The lassopath function specifically gives me the coefficients at different values of the regularization parameter, alpha. The lassopath function is an algorithm that helps us find the best coefficients for a linear regression model, while simultaneously performing feature selection. It does this by iteratively trying different values of the regularization parameter, ALPHA. These are different values of the regularization parameter ALPHA that the lassopath function uses to compute the regression coefficients. A larger ALPHA value results in stronger regularization, pushing more coefficients toward zero. These are the regression coefficients calculated by the lassopath function for each value of ALPHA. They represent the impact of each feature on the predicted outcome. I observe that as ALPHA increases, some coefficients become exactly zero, implying that the corresponding features are deemed unimportant and are removed from the model. These are related to the optimization problem the lassopath function solves. They are not directly interpretable as model residuals, which are the differences between the actual and predicted values. This is the central question of the problem. It asks about the relationship between the regularization parameter ALPHA and how it influences the coefficients in a lasso regression model produced by the lassopath function. This statement is correct. Increasing ALPHA strengthens the regularization, shrinking all coefficients towards zero, but some will hit zero before others. It's like tightening a net. Some things fall out first. This statement is incorrect. The duals are part of the optimization process and don't directly represent the residuals. This statement is also correct. The lassopath function, by shrinking coefficients to zero, inherently performs feature selection. This statement is incorrect. The ALPHAs are usually sorted in descending order. I see the lassopath process as a journey where we explore different levels of regularization. Think of it like gradually turning up the dial on a noise filter. At each step, I'm adjusting how much I'm penalizing large coefficients. Alpha is our regularization parameter. As I increase alpha, I am increasing the penalty on the size of the coefficients in my model. This forces the model to become simpler by shrinking some coefficients toward zero. It's like using a really strict editor, removing unnecessary details and making the model more concise. As I increase alpha, I observe that all coefficients shrink. However, some shrink faster than others. The ones less important to the model reach zero first, as they are less important in explaining the data. It's a competition, and some coefficients reach the zero line faster than others. When a coefficient becomes exactly zero, that means the corresponding feature is eliminated from the model. This is a byproduct of how lasso works. It performs automatic feature selection. It's like the model is saying, this variable isn't helping me predict, so I'm getting rid of it. I see you're working with lasso regression using scikit-learn's lassopath function. This function is fantastic for finding the best regularization strength for your model. It does this by trying many different values of the regularization parameter, alpha, and providing the corresponding model coefficients. Okay, so we're observing something interesting. As we increase alpha, some of the coefficients in our model are becoming exactly zero. This is a key characteristic of lasso regression. Let's figure out what this means. This is absolutely correct. Lasso regression uses a penalty term proportional to the absolute value of the coefficients, L1 regularization. Increasing alpha makes this penalty stronger, pulling all the coefficients towards zero. However, coefficients with weaker effects on the model will reach zero first, like a race where some runners are faster than others. That's a great observation. When a coefficient is exactly zero, it means the corresponding feature is essentially removed from the model. So, lassopath implicitly performs feature selection by setting unimportant features' coefficients to zero. That's a pretty powerful feature. This statement is incorrect. The lassopath function typically outputs alphas in descending order. It starts with a large alpha and works its way down, gradually reducing the regularization strength.